Yeah, welcome to the second session of the CAiSE 2021 conference. My name is Stefanie Rinder-Lehmann and I'm the session chair. I'm very much looking forward to a very interesting session on a very timely and exciting topic, which is NLP and text. And I'm looking forward to 3 inspiring talks and also a discussion with the audience. And for the discussion, I just want to mention that there are 2 ways of asking questions. So either you can raise your hand virtually, or you can also post questions in the Q&A. And then without spending too much words, I want to directly introduce the first speakers and paper. The first paper is on extracting semantic process information from the natural language in event logs. And the authors are Adrian Rebmann and Han van der Aar. And the speaker is Adrian. And so please, Adrian, I want to give the floor to you. Looking forward to a presentation.
Yeah, thank you. I cannot yet share my screen because someone else is. Yes. All right, so you should see my slides now. All right. So yeah, thank you for the introduction. My name is Adrian. I'm a PhD candidate at the University of Mannheim in Germany, and I'm happy to present our work on extracting semantic process information from the natural language in event logs. So to get right started, many process analysis techniques depend on a very specific semantic information to be available in event logs. So if you consider social network analysis, for example, this needs information about the resources or the roles that are active in a process. Also, if you want to analyze a process from an object-centric perspective, you need information about business objects that are handled within a process. And the problem in this regard is that this semantic information is often not readily available. This is in particular the case for real-life event logs. And there are 2 main challenges in this regard. The first one is that this information might be contained in unstructured textual attributes, where there are a few examples, all from real-life event logs. In the first one, you see that there are 2 actions, draft and send, and also business object, request for advice. Also, in the second example, there is even resource information in the single textual attribute value, which is the stakeholders in this case. Also, there are all kinds of event labels with other semantic information, such as status information. In this last example, declaration final approved by supervisor, we see that there is this final status information that refers to the approval or to the approved action. And there's also resource information. Again, this time it's an active resource, which is the supervisor in this case. The second challenge is related to the fact that this information might not be contained in standard attributes. So there is this the well-known XCS standard, and this semantic information might not be contained in specific attributes. So if you have, for example, an attribute that is called is cancelled, which refers to a status of a business object, there is just no standard available. Also, this is the case for something like docked type, which refers to a specific document that is being handled, so a business object. And there's also cases where you actually have a standard attribute available, but this is just not used, like in this assignment group. And so our goal here was to automatically identify and extract semantic process information from natural language attribute values, but also the attribute names of events in event logs. And we refer to this pieces of semantic information as semantic roles, and we focus on these semantic roles in our work. So we're looking at business objects, as we saw, like purchase order or application, status information related to these business objects, actions, and status information regarding the actions, but also the resource perspective, differentiating between active and passive resources. All right, and we propose a three-step approach to achieve this goal. And basically, this takes as input any event log. Then we first apply some data type categorization step, where we basically split the different attributes that we have in the event log into textual, miscellaneous, and other discarded attributes that we know not consider further because they're unlikely to contain any of the semantic information we're interested in. In the second step, we check the textual attributes per attribute value and perform an instance level labeling, where we basically take each individual textual attribute value and assign the semantic roles we're interested in to particular parts of the attribute value. And in the third step, we handle miscellaneous attributes on the attribute level, where we assign a semantic role, if applicable, for example, to a whole attribute that is called assignment group, for example, or is canceled as the business object status. And basically the output is an augmented event log. So we have the same attributes that we had before, but now we have additional attributes capturing the different semantic roles. Right, so a bit more detail about the steps. So on the first step, again, we mainly want to identify textual and miscellaneous attributes. And we first apply some pre-processing steps where we look at the values of the attributes and omit all kinds of special characters and also white space and numeric parts. And then we can already filter out something like real valued numbers or timestamps that are unlikely to contain semantic roles. And we then, if we have string content, further look at part of speech tags to find out if there is actual diversity in the natural language. And depending on that, we assign this to the textual or miscellaneous attributes. There's also some examples here. So this first one is clearly natural language and textual. So we have verbs here, we have nouns. This is not the case for this user, for example. So we only have basically a single noun present. So this is not very diverse natural language, which is why we would assign this to the miscellaneous attributes. And then, as I said, timestamps and, for example, something like payment amount, which are real valued numbers, are discarded for further analysis. In our second step, the instance level labeling step, again, the goal is to assign the semantic roles to parts of textual attribute values. So for this, we use a pre-trained language model, which we basically fine-tune on a text tagging task. This is based on BERT, which was proposed by Google in 2018. And this can be used to train on a very specific task, and we train it on the task to tag our textual attribute values with the semantic roles that we are interested in. And then there's some post-processing as well, where we merge tokens that are consecutive and labeled with the same role. To quickly show how we obtain this language model, so we have the pre-trained language model and use annotated event labels from real life event logs on the one hand, but also a large collection of activity labels from process models to fine tune the model. And once we have that fine tuned language model, we can then input our individual textual attribute values, which are then tagged with the respective semantic roles. So in this particular example, we would assign the action role to send, the business object role to the sign decision, and there's also some unnecessary part here. And then also stakeholders would be assigned a passive resource role. In the third step, again, we focus on the miscellaneous attributes on the attribute level. And we basically have two methods here. One is based on the attribute names, and this is particularly interesting for non-textual attributes. And the idea is that we look at the semantic similarity to labeled attribute names of other event logs that we know. So to make an example, we might have an attribute that is called product, and then we can check for the labeled attribute names that we have, which is the closest related to product. In this particular case, we would see that business object attribute, which is called item, is very closely related from a semantic perspective, which is why we would then assign also the business object to that one. Second method is again based on attribute values, but focuses on noun-only attribute values. And this is particularly for cases where we found that the language model has a hard time to differentiate between semantic roles. And this is the case if there is a lack of context available. So if you have an attribute like that has values like this, so only basically user, vendor, user, and so on, the language model would have a hard time to say if this is actually resource information or if this is a business object, since it is a standalone noun. And therefore, we propose to use template sentences that contain the semantic roles we're interested in and basically replace the roles by the unique attribute values of the attribute that we're currently looking at. So in the example, we would have this template sentence: customer confirms that paperwork is done. And so this would be active resource. Then we would see that there is an action, there's a business object, and there's also a status referring to a business object. We would then replace, for example, the action by vendor, and then input the created sentence into our language model, which would then give us a confidence of how likely it is that this is indeed an action, which would in the case at hand be very low. On the other hand, if we replaced the active resource by vendor, we see that the sentence vendor confirms that paperwork is done would get a very high confidence for this being an actual active resource, which is why we would then assign the active resource to this attribute. All right, then a few words about the output of our approach, which is an XCS event log that contains additional event attributes. So in the example here, we only show basically the activity or the event label of this event log. And our approach would extract, in this case, action, status information about the action, and business object, and also actor information, which is all contained in a single unstructured textual attribute. Then there are a few choices one can make. So if you recall from the initial examples, there was the case that we had multiple actions in a single textual attribute value. And then the user of the approach can basically decide if he or she wants to capture this information in a single attribute, or if the attribute should be indexed like this. Also, something that can be done is we can consolidate Boolean status attributes into textual attributes. So if we have an event log that initially had something like is canceled and is closed, we could just as well consolidate that into a business object status attribute, which would then contain textual values like is canceled, is closed, or just no value. Right, so we evaluated our approach based on 14 real-life event logs. We set this up as a per log cross-validation where we train our models on 13 logs and always test on the 14th. For the instance level labeling step, we fine-tuned our language model with about 12,000 unique activity labels from process models, and then the unique event labels of the 13 training logs. For the attribute level classification, we trained on the attribute names of the 13 training logs, and we measured performance in terms of precision recall and F1 score. And we also compared against a baseline, which is a state-of-the-art activity label parser that is also capable of extracting actions and business objects from activity labels. The results for the instance level labeling step look quite good throughout the semantic roles we consider. So we are at about 0.9 F1 score throughout the roles that we have. One thing to consider is, for example, if we have not a lot of context with our attribute values, such as in this example, denied and in progress, it's very hard, also for a human, I would say, to say if this refers to an action or business object. So this is one challenge. And for the baseline, we can say that we outperform the baseline, and main reasons for that where we found that we can handle multiple actions very well, but also very long business objects that that span across multiple nouns are well recognized by our technique. The attribute level classification, yeah, we have very good results for active resource and action status. This is partially due to the standard XES names being used, but also we correctly recognize non-standard names, such as this assignment group or department, something like this. And so we can say that the semantic similarity-based approach looks promising. However, we currently have quite a small training set for this particular step of the approach, especially for business object and business object status. Then I also want to highlight some application cases that can be realized using our approach. So first would be event class refinement, where, so this is all based on the BPI Challenge 2020 event log, the permit log to be more specific. And in this particular log, we see that in the event label, we have also resource information contained, which is actually bad practice if we also talk about process models later. So what we can do is we apply our approach and extract a business object, action, and active resource in this case. We can then construct a new event label and move this resource part to a separate attribute. And then in this way, we can reduce the number of event classes from 51 to 20, which if considering applying process discovery to this would yield simpler process models. Then a second case would be object-centric analysis, where we can apply our approach on the event log and then select events that refer to a specific business object. So in the example, we would take the events that refer to declaration, and then we can discover a directly follows graph, for example, which would then look like this. And in this way, we can see how this particular object is handled in the process. And we would also spot some irregular, or what looks suspicious at least, that this final approved was followed by rejected for the declaration. So to sum up, we showed that our approach accurately extracts semantic roles from event data. We showed some possible application cases, which were the event class refinement and object-centric analysis. I would like also to point to our code, which is on the one hand linked in the paper, but we also created an additional Python package, which is easier to install and can also be used to label single textual attribute values. So if not the full approach is needed. And as an outlook, we have been working on also the natural language-based detection of semantic execution anomalies. So basically what is also seen in this example, to find anomalies from a semantic perspective in event logs. And we also are currently working on event abstraction based on the semantic information that we can now extract. So based on common business objects, for example, similar actions and so on. Yeah, and with that, I would like to thank you for your attention, and I'm looking forward to your questions.
Yeah, thank you very much for the very interesting talk and also for the great time management. So questions, please. The floor is open. So maybe I, again, if maybe someone joined later, so you can either raise your hand or also post questions in the Q&A. But maybe this takes some seconds, then maybe I start with an icebreaker question. So yeah, it was really interesting, and I see that you could do some kind of sanity checks on the logs. So it seemed to me that you are currently looking at the activity labels mainly, but in logs. So for example, we had sometimes some teaching logs recorded, and there we had also other textual information, like for example forum posts or something like this. Would you see that this could be also an interesting application for your approach, so that you also look at other data that can be textual in your log?
Yeah, so thanks for the question. So yeah, we focus a lot on event labels, basically in the second step, but also on other attributes in the event log in this third step. But yeah, of course, this could generally also be applied to other textual data that is created through the process or execution of a process. Yeah.
Mm-hmm. And what could you learn from that then, for example? So I learned from the event data, it's very interesting that you mentioned, for example, like this is also a validation step about bad modeling practice. So to put, for example, the resource information into the activity label and these kind of things. What else could we maybe learn from other attributes?
Attributes in the event log or additional data that we...
Additional, yeah, within the event log maybe first.
Yeah, so as I for example showed with the example here, that so these are basically not event labels. Yeah, no, not event labels, right? So these are event attributes that are just Boolean flags, and we could still infer or learn information about the status of a particular business object. I'm not sure if that's what you
for example, okay, thank you. And now we have already questions queuing up in the Q&A. Nice. So the first question is, originally part of speech taggers have been developed for analyzing complete sentences. How good does part of speech tagging work when applied to short phrases as they occur in event logs? And did you experience any difficulties? Which part of speech tagger worked best for your purposes? This is already 3 questions in one. I can also repeat.
Yeah, I think I got the main part. So yeah, so we basically only use this part of speech tags in this particular steps, and this is just to make sure that we are not looking at something like this in our second step, because that is not so interesting. If there's only a single noun, actually, if you remove all these numbers, it's not necessary to analyze this with a language model. And we basically used state-of-the-art part of speech tagger that is from Spacey. I don't know if that matters in this case, but yeah, it basically says, it gives us information about if there is some diversity in this text that we're looking at. And that's actually the only time we use this part of speech tagger. And for this particular purpose, this worked quite well.
Yeah, this is also connected to the second question in the chat. So this is also, again, asking if the approach is just applicable on short sentences or also on large texts. You want to comment further on this?
Yeah, so we use it here for very short texts, indeed. So actually this BERT model is capable of handling very, very long text also able to remember context from very far apart in the sentence, but actually for the event labels that we have, this works very well, as also the results show, especially for this part that was based on bird. The results were quite good, actually.
Mm-hmm. And then there's also a question regarding BERT, if you speak about BERT now. So how much data did you use for fine-tuning BERT?
So this was based on these 12,000 unique activity labels that we annotated manually with the semantic roles that we're targeting. And then also, of course, we add some of the annotated labels from the event logs in the evaluation as well. So this is basically the data we fine-tuned on. We also had some textual process description, rather short ones, but longer than common activity labels.
Mm-hmm. And how long did the training take? So BERT is known to be quite large.
So this is not, we did not retrain this model, we only fine-tuned it, which is faster. And if you have GPUs available, it's actually quite fast. Also, this 12,000 is not from the perspective of this particular model, it's not so much data. So this was actually quite fast. I really cannot remember how much a single training run took, but it was definitely in the hours scale. Yeah.
Mm-hmm. And did you think of trying smaller, less accurate models?
Language models, you mean? So
I think so. It's a question from the chat.
So we just used the base version of BERT for this, and this worked quite well. Of course, we can use some reduced variant of this. There's all kinds of these available. What we also would like to do that is not maybe related to the particular question, but we would also like to do this in a multilingual setting, because we now train this on the English, the BERT that was trained on English. Yeah.
Mm-hmm. Okay. So I think this is also then kind of answering, there was again a question about BERT and other language models. Yeah. And then we have another question. Could the proposed approach benefit from the usage of unsupervised approaches for tagging? Also, thus not requiring a preliminary tuning or training phase.
I'm sorry. Can I actually read that somewhere, or no? Right.
I don't know if you can access. So I can repeat it. If your approach could benefit from the usage of unsupervised approaches for tagging, such that you don't require a preliminary tuning or training phase.
So I would say for the particular scenario, we have quite a good idea of what we are interested in, which I would say would make unsupervised approaches very hard to get this kind of accuracy. But I'm happy to also look into that if you have any pointers.
I mean, maybe I ask Xiang, can the speaker see the Q&A? I don't know.
Yes, I can make him see the.
At least I can see it. So I'm a speaker.
Okay. Yeah.
Sorry.
So then it's probably easier if you can also read it in parallel. So yeah. Okay. Right. So I just take a look if there are more questions. I don't see any. Yeah, but it was a really interesting discussion. And then I would say we thank again the speaker. And now I'm looking forward to the second presentation. And the second presentation is on data-driven annotation of textual process descriptions based on formal meaning representations. And the paper is authored by Lars Ackermann, Julia Neuberger, and Stefan Jablonski. And the presentation will be delivered by Lars. So please, the floor is yours.
Thank you very much for the introduction. So let's get started. 1 second. Okay. So probably all of us or most of us know that business process management can be described by means of so-called lifecycle models. This is an example of such a lifecycle model, which incorporates multiple steps which are incorporated during the business process management. And especially we are interested for this talk in the first two, where is it about creating business process models that are then somehow configured to implement them in a particular workflow engine, to create work lists and all this stuff and so on. And creating such formal models requires a rather huge amount of time. And this is the issue we are going to work on in this talk. And the sources for creating such models are, of course, somehow arbitrary, but in many cases, you take notes in interviews, you interview the people who are participating in processes, or you take quality management manuals as the basis for creating such models. But doing that takes up to 60% of the time spent in the whole process management. And yeah, this is quite a huge space for optimization to accelerate the creation of such models, or to see if there is an alternative for that. So there are also some strong arguments in the literature why natural language text, for example, such quality management manuals and so on, are valuable in particular situations, because in some cases such natural language texts are more adequate for the particular purpose than a formal model. At least, for example, some end users might not be familiar with the formal notation of business process models, so it would be more convenient to show them a natural language representation of the process. So there's a justification. Let's assume that we have natural language text and we want to keep that alive. We don't want to avoid natural language text. But if we want to go on in this shown business process life cycle, we have to transform it somehow into this formal representation. But in some cases, we don't need a whole business process model for particular purposes and applications. We can also make use of annotated text, which is the same text that is shown here at the top of the slide, but enriched with further information, which gives you, or gives some algorithm an idea what some pieces of text are about. So, for example, it marks actors, roles, actions, data objects, and so on. We've also seen a couple of examples in the previous talk. And one application scenario for annotated text is, for example, formal reasoning, which can be used to check properties of a process, which would be usually only possible if we have a process model available. So the annotated text here would be a possible replacement for a process model. And the question is now, how can we annotate such text? And we do want to automate this task, because this is usually cumbersome and time consuming. So how can we automatically annotate natural language text? And so to summarize it, the goal is we take natural language text, plain text as input, automatically annotate this, and the result would then be a text which is enriched with information that classifies pieces of this text regarding relevant for the business process domain. So how can we do that? And to be more concrete, which features can be used by some algorithm to perform this automatic annotation? So we can simply look at the words, but obviously this is not the best choice in all cases, obviously, because looking only at the words covers a couple of issues, and one of them is the variety. There's a huge variety where a word can occur in a text with different articles, for example. So it's really diverse, and it's hard to get the complete variational complexity of the word representations in a text and to associate them with a particular meaning in business process management terms. So ambiguities is the next thing. We have syntactic and semantic ambiguities. Does marks in issue mean a verb or a noun? Of course, this depends on the context. But if we only look at the words, we don't have any context, obviously. So the next thing is, in a particular sentence, does a particular word mean an actor? Who's the actor in a particular sentence? Of course, we know that the author marks the issue. The author is obviously the actor. But how can an algorithm know that? And in order to find that out, to figure that out, usually a couple of further additional information sources are used to disambiguate these issues or to solve these issues. Examples for additional information sources are taxonomies, ontologies, part of speech tags, as we've already seen in the previous talk, word embeddings, which give us sometimes contextual information about words and the semantics. And one specific thing which is used in most of the related work is syntax parsing, means analyzing the syntax of a natural language sentence. Why is using syntax difficult or somehow dangerous? Let's have a look at the small example. It's not really necessary that we understand what this depiction completely means. It simply shows a syntax analysis result of a natural language sentence, which gives us first the part of speech text. These are the boxes above the different words here. And it forms a graph which shows the dependencies, the syntactic dependencies between all of the words that are part of the sentence. And this structure gives us an information about the relations between the words. And for that, the meaning here is that an object is somehow modified. The author takes a pencil means the pencil is somehow modified, the location changes. This is fine. And the same is also expressed with a second sentence, which is in passive voice this time, which shows a completely different structure here. And if we consider this, we have a difference in the structure, which we really don't want to have, because we are not interested whether it's a passive and active voice. We are just interested in the meaning that the pencil is moved somewhere else or taken by some participant of the process. So that is usually not what we want to see for our annotation issue. And the other way around, we have sometimes the same structure which describes different things. So the author takes a shower is obviously not meaning that the author takes the shower somewhere else, but he's showering. So this is where we have the same structure but a different meaning, which is again somehow ambiguous. So this is why syntax is not the best choice in many cases, and we will come back to that issue on the next slide. First, the related work solves this annotation issue usually rule-based. So most of the related work provides an approach that is rule-based. They use the information sources shown on the left-hand side and many more. Some are also machine learning based. And we want to argue for an AI-based, as it's shown here, more concretely a deep learning-based approach, which is data-driven. And why a data-driven approach can have many benefits, we will see at the end of the talk, hopefully. So I said on the previous slide, there are a couple of issues with syntactic parsing. And what we do basically is to replace syntactic with semantic parsing. So what is now semantic parsing? Semantic parsing is simply transforming a natural language text into a formal meaning representation, means a formal machine understandable representation of the sentence's meaning. what are the benefits of doing that? This abstracts away from specific syntax information. So we are not interested in active passive voice like it was shown on the previous slide. So this is one thing semantic parsing can abstract from. And since it's semantic parsing, it already disambiguates meaning and reduces therefore the complexity of subsequent tasks that might use the meaning representation then. So it already gives some information what the meaning, the very basic meaning of a sentence can be. Of course, this is very abstract, so let's have a look at a particular example. We have on the right-hand side a particular formal meaning representation, which is based on a principle or an approach which is called universal conceptual cognitive annotation. This is simply a language which is able to which enables you to represent a sentence regarding its meaning. And what it says here in principle is that we have a certain process. This is why this arc here is marked with P. So there's something happening, and we have two actors in this process. One is the author, and the other one is the pencil. Of course, it's not really an actor, but it's rather a participant, like it's participant is the right word for that. So it's not really acting, but it's a participant of this process. And if we have a look at the same parse tree for a different sentence, the author took a shower, very similar to the example on from the previous slide, we see here that there is no second participant anymore, because it's not really about modifying an object, but it's rather about describing the process of showering. So here we get already this disambiguation of meaning somewhere, and we have a different structure now where we have with syntax parsing the same structure. So this is where semantic parsing has one of its strengths. Why did we choose UCCA in favor of other alternatives? It's independent from any particular domain and language, and this is not this does not hold for many other examples of such formal meaning representations. So this is one of the main reasons, and the second main reason is they already provide predefined cognitively motivated categories which look very familiar regarding the process domain, because they already disambiguate or distinguish between processes and states. So this means they analyze whether a sentence is rather about something happening or describing something which is a state, some static information. But still, the structure is not enough. We need disambiguation. Why? We have here an example. The author provides information. Okay, this is somehow can be considered to be an action. And on the other hand side, we have this sentence provides information that I would rather say this is static information, but still we have here some kind of an actor, because we have here this participant relation, and the center word of this participant relation is the sentence, and it's somehow the same structure, but a different meaning. So we need further features to disambiguate these meanings, and we will see these features on the next slide, or at least I will mention them. So putting everything together, this is our whole approach, which it looks very detailed, but I will briefly introduce everything. So the input is again raw text, natural language text, which is first tokenized, so split up into pieces, which are usually words or groups of words. And then they are tagged with para-speech tagging. And this is the result of the pre-processing phase. The result is then handed over to the next phase, feature extraction. Then we perform the semantic parsing I've just talked about on the previous slide. Here we can make use of some pre-trained semantic parsers, which achieve a high quality for producing such semantic representations. And semantic those semantic representations are graph structures. The terminal nodes are the tokens, and the inner nodes are the nodes that classify the role of the leaf nodes in this particular sentence, the semantic roles. again, we have to disambiguate the structure still. So here we enrich the nodes, all of the nodes, with further information. These information can be, for example, part of speech text themselves. We have already them available. We already have them available, and word embeddings, such as we have seen bird in the previous talk, word to vec, and other things could be used here, glove. And yeah, we use this as a feature vector, which is associated with each of the terminus symbols. Okay, now we have a graph, and we want to produce a data-driven approach, and this is done here by using a graph convolution network. This graph convolution network is a network architecture that is able to take a graph as an input and to classify, to assign a class to each of the tokens, which is actually our task, because annotation in our case means we want to associate a token with a particular class. So this is what annotation means to us. And this is possible with graph convolution networks. So it's a classification task on token level. Okay, so the core features of our approach are we use formal meaning representations instead of syntax representations. We enrich the formal meaning representations with additional custom features. This was the part of speech tag example and the word embeddings. And what we also can do is to apply to different annotation schemes. This is usually not the case in most of the related work. And it's data-driven, meaning that it's somehow also noise resistant, which usually which mainly comes from the graph convolution approach, of course. And it reduces the cognitive load for creating such an annotation system, because here we don't have to define any rules how to extract or how to annotate the text, but we can simply provide examples how a correctly annotated text would look like. And there's a magic machine which learns that and is able to perform this labeling afterwards by itself. So I think we have a couple of minutes left, so I can briefly talk about the graph convolution network. As I already said, we take semantic parsing result. So this is the formal meaning representation of a sentence which starts with the author takes something, the pencil, and we transform that into a representation which looks like it's shown here, where the feature vectors are associated with the particular tokens. And then this graph is converted into multiple adjacency matrices, one for each edge type, by the way, and one feature matrix, which is simply a horizontal concatenation of all of these feature vectors. And the combination of these two things are then handed over to the graph convolution network, which is then able to produce a probability distribution over all different classes for each token. So it means we can then select the class with the maximum probability from the resulting matrix the graph convolution network produces. So, okay, the question is now, how well does this work? Is it performing well? And here we want to also make some advertisement for some alternative measures that are not so frequently used in literature. Actually in our domain, but in the computational linguistics domain, they are frequently used. The issue I talk about is that in some cases, we produce an output which is shown here on the left-hand side. The gold standard says, okay, the author takes means the author should be marked as an author, but our annotation system says, okay, this is an actor, but that is not part of this label, so skip that. And so, of course, this is somehow a mistake if we want to have an exact match between the gold standard and the prediction, but we have still some valuable information here which we can use for whatever, for semantic analysis, for creating a business process model from the text and so on, or formal reasoning, as I said at the beginning. So the question now is, can we somehow judge this a bit more smoothly, not so strict? And there are a couple of ways to do that. One of them is partial matching, which means, okay, we still give some points if we match at least something. And this something in terms of partial means if we match the left or the right boundary of a whole span of a labeling, we still give a score of 0.5. And we can also give the same score if we just match one token within that span. So in this case, we would also achieve a score of 0.5, a count of 0.5, which is not 0 anymore. So it's a bit better than, because we already have some valuable information here, which should be taken into account. Another thing is we can simply split up everything into individual tokens and judge each token individually, which means we don't have any connected fragments for labeling anymore, but we have each token individually and say, okay, is this the right class for the token referring to the gold standard, yes or no? If yes, we give 1 to the count, otherwise 0. So these are some different metrics we can use, and based on that, we can calculate the probably well-known metrics, precision, recall, and F1. So the data sets for our evaluation are shown here on the left-hand side with 4 data sets basically of different sizes and different domains. We have cooking receipts, maintenance manuals, and some mixed domains. For example, here we have also document management and quality management. And the amount of sentences, as I already said, differs really a lot. We have here only 200 sentences, 250, and this is our newly created data set we created just for this for this paper, for this approach for the evaluation. What we analyze here on the right-hand side is we compare ourselves to a state-of-the-art rule-based approach. So this is an approach which defines rules on syntactic structures to perform the annotation task, and on the right-hand side, ours. This is our approach as we've shown on the previous slides. And here we see that we almost achieved the same accuracy on the data set from this QCD data set here. Yeah. But if we move to another data set which contains more noise, and this is the main difference between these two data sets, we see that the accuracy of the other approach decreases, while we have rather a constant quality of our results. And this is somehow showing us the noise resistance I was talking about. A second part of the evaluation was about how valuable are the additional features we use for disambiguation. And here I have to say we have a couple of tasks which we have to solve, because I've also mentioned we are able to deal with different annotation schemas. This means in one schema, for example, an actor might be called actor, and in another schema it might be called participant, or in some schemas we have an event, in others we don't have any events, and so on. So this variability can be also incorporated with our approach. And one schema requires that we first classify a text, a sentence, if it's an action, describing an action, or some static information, which is here meant to organize actions in terms of the control flow, which means we have sequence relations, we have concurrency, and so on. And so this is the first decision, which is part of this task, is made towards whether we have an action description or a description of a control flow construct. And here in the clause semantic relation, we further analyze the control flow descriptions, whether they are really sequences or concurrency. And here we have semantic role labeling, which is analyzing the actions and extracting the information. What is the action? What is the actor? What are the objects that are somehow modified and so on? Okay, so these are the different tasks, and we have also the results for that here. We see in many cases that the structure already gives a good baseline for the classifications, at least for these tasks here. But here we need further disambiguation because the accuracies really drop to a very low value. And what we also observed during our analysis is that, of course, we can, for example, use BERT. We also experimented with BERT, but BERT has rather a huge feature vector, which requires much more training data. But as we have shown here, we only have 250 sample sentences to train the whole approach somehow. And this seemed to be not sufficient to use such high dimensional feature vectors that are provided by BERT. So this is why we rather relied on GloVe and Word2Vec, which are rather low dimensional. So there are also a couple of limitations. We are not able currently to extract relations. This is currently a work in progress because so we have to extract relations between the entities we identify so that the actor is the actor of a particular activity. So the relation between these two pieces, we want to extract two. We can only classify one. We can only assign one class per token. And we also want to improve our evaluation regarding dependency parsing. We already said that semantic parsing might be superior somehow, but we also want to prove that with our own investigations. And we want to use diverse features, not only part of speech tags and word embeddings, and also some advertisement for future work. We want to extend our dataset with data augmentation because, as we've seen, the dataset is rather small, and we already made some good progress in extending the dataset with artificially created data. So that's it from my side. Thank you very much.
Thank you very much for this very inspiring talk. And I already see a first question here in the chat. So this is a really promising approach. And actually, there are two questions here. So the first one is, what are the process dimensions you are discovering in your process annotations? Yeah, so simple events, flows, loops, business rules, etc.
Yeah, okay. As I already mentioned, this depends a bit on the annotation schema because the approach is able to deal with different annotation schemas. And regarding the, maybe I should go back to a slide. Okay, it's shown here. So there's this ATDP schema, and there we are able to identify actors, actions, business objects, and also events, but the events were somehow underrepresented in the data set. So the algorithm was in fact not able to learn anything about this token class. But in principle, it would be also possible to identify these events too. As I already said, we are not able to identify relations. Something like loops, for example, would require to no, I'm wrong, sorry. Loops we can identify, but not in terms of a relation. I mentioned here the class classification, and one particular class in this class semantic relation extraction is about loops. So here we can also identify loops.
Mm-hmm.
Okay, so this
all right, and then
Did I get everything?
And the second question is, how much samples, so like in the number of sentences, for example, would you need to start having a performing model using semantic parsing frameworks like UCCA?
Okay, so if I understand it right, this means we have already available a well-performing semantic parsing framework, and the question is now how much samples do we need to start with our approach, right?
Okay. I think I can elaborate if you like, if you allow me. It's just because
sure.
I look at the size of the data set that you started with, and I know Kishpi's data set is like for 203 label sentences, and yours is 250. But I was wondering whether this is enough for deep learning method, the ones that you're using.
Yeah, clearly this enough is a bit subjective somehow, and otherwise, on the other hand, not. It is enough to achieve the scores we've seen, let's say, yeah, but enough for productive application, I would say no, because yeah, all of us probably know that deep learning is really data hungry, and this also holds for our application, because the graph convolution networks have a rather huge size, and especially if we want to incorporate more powerful feature vectors from, for example, BERT, which uses context information for each token, we require definitely a higher amount of training data for that. And this is why we also mentioned in our outlook that we want to enrich our data set with data augmentation. So to answer it in short, no, the data is not sufficient.
All right. Yeah, then thank you very much. So in the interest of time, we have to stop right here, but I think also there could be, of course, follow-up discussions. So thank you again for the questions and for the talk. And then I would like to ask the speaker of the third presentation to get ready. And the third talk is about an NLP-based architecture for the auto-completion of partial domain models. And the speaker is Loli Burgueño. And yeah, please, the floor is yours.
Thank you very much. So yeah, let me present my work. Okay, so our work focuses on improving the task of domain modeling. I don't think I have to go into deep details about what domain modeling is in the CAiSE community, but let me at least say that the goal is to take the informal descriptions of a business or domain and to come up with a structured and unambiguous representation that leaves out all superfluous details and also uses a concrete and in most cases a formal notation. So the motivation of our work was that we wanted to promote and facilitate the creation and manipulation of domain models. We are aware that there are a wide variety of languages such as UML, VSL, entity relationship, diagrams. There is also a wide variety of tools. To name some of them, we have Magic Draw, we have EMF, we have DIA, we have Papyrus, but still there are, domain models are usually created by hand. So we thought that maybe we can help the users and assist them when providing some suggestion while they are creating their domain models. And this comes data. Now we live in the era of data, and as soon as we start modeling a domain, we of course have the requirements, but we also have, in most cases, technical reports. We have slides provided by the stakeholders. We have sometimes a recording of the interviews that we had with these stakeholders or experts. And we not only have this, but we also have a lot of information available from Wikipedia, from Google News, from Reddit, and this translates in a bunch of data that we could exploit. In our approach, we distinguish these two different types of data, one coming from the contextual domain, which we call contextual knowledge, and the other one is general knowledge. Many people say that the data has a better idea, usually. We're not that optimistic, but we say that data may have a better idea in some cases that may help us develop our models. So in our scenario, we have, for instance, a modeler, which is manually creating a domain model. And our idea was, since we have all this bunch of data, and we are also aware that there's this field named natural language processing, which is a subfield of artificial intelligence, and some of those techniques overlap with the machine learning. Why don't we try to exploit this big amount of data that we have to assist our users and provide meaningful suggestions to them? And that, we hope, makes them more, happier. So let me now go into detail of the different steps of our approach. So first of all, we take all the domain documents that we have. In the case that we have audios of the interviews, we have to transcribe them to text. And in the end, we have a lot of text that we pass to a text processing algorithm, which removes stop words and punctuation signs and so on. And after this preprocessing, we have a domain corpus of text. Then the NLP components come into play. We have two main components, two main NLP techniques that we use. The first of them is the methods for word embeddings. So this method, what we do is they take the corpus of text and analyze the frequency in which words appear together. So there's defined a distant function, and words that appear more frequency together have a closer distance among themselves. And with this, we train, given our domain corpus of text, we train a contextual knowledge, and we have one contextual model. And we complement this contextual knowledge with the general knowledge, because we know that when we have the requirements and interviews and so on, usually there's some implicit knowledge that we humans are able to understand, but machines don't. So yeah, we try to complement those gaps in the contextual knowledge using general knowledge. And in our case, we have used Wikipedia, but we could have used any other source of general knowledge, like as I said, Wikipedia, Google News, or whatever. And in this case, since the Wikipedia, we took all the entries from Wikipedia and used this pre-trained model. We haven't trained it. That could have taken like hours and hours, but yeah, we are using the pre-trained model by Stanford University. And our other component is the morphological analysis and lemmatization. We use this component to come up with the root of some words, and also to know if they are verbs, if they are nouns, if they are adjectives, adverbs, like the post tagging of words. So right now I have explained our NLP components, but these NLP components are only able to deal with text. But text is not enough for us, but we have to provide a model recommendation, like we need to add this association, we need to add this. So for this, we have created a model recommendation engine that uses these NLP components. So let me explain this part with an example, and let me assume that we have this domain model, which is represented by a class diagram. And we have a partial model that is under development that we have, that it has the two classes, one pilot, one flight, and a relationship between both of them. So the first step of our approach, the model recommendation engine, is to slice these partial models. We have to slice it because we have to focus on the different parts of the model to provide meaningful recommendation for each specific part. So right now we extract different types of slices. We extract one slice per each class in the domain model. We extract another slice per each class with their dangling associations. And another type of slice is for each pair of classes, we extract the classes and the associations. In this example, we don't have attributes, but we would also extract the attributes in the kind of slices 3, 4, and 5. And then for each, I mean, the goal of slicing the model is that each type of slice is good for providing some different recommendations. So once we have sliced the partial models, what we do is to query the NLP models. So from each slice, we extract the name of the class, the name of the association, and the name of the attributes. That gives us words that we use to, as I said, to query these models. Once we create this model, as I explained before, given the nature of them, we obtain words that usually appear together frequently in the same context, which we assume that they are words that are usually related. So in the example of the first slide, which contained the class flight and the concept flight, the recommendations given by the NLP models are flights, plane, pilots, pilot, flying. You can see that some of them are repeated. We have plurals, we have verbs, we have repeated words that are already in our partial model. So the next step is to refine this list of concepts. For instance, we remove plurals. We differentiate which ones are verbs, which ones are nouns, and so on. And now that we have refined our set of concepts, we build the actual recommendations that we are going to provide to the user. So as I said before, depending of the slide, we recommend different elements to add to the model. For instance, for each slide, which is composed of a single class, we recommend associated classes, or we recommend to add attributes to that specific class. So imagine that for the slides that I showed before, the recommendations that we build are add a new class named plane, add a new class named airline, and add a new class named airplane. There would be more that would be about attributes, but I mean, there's not the point of this presentation to present all these details. You can check them on the paper. So let us assume now that the user has decided to add a new class named plane to the model, and at that moment the domain model is updated, and now we have this new class there. And our process doesn't finish here, as we also store the feedback from the user. For instance, we register that our user, given the recommendation that we have given to him or her, has accepted the word plane. We could also register and store the recommendation that the user has ignored, and we will use this information to provide better recommendations in the future. For instance, the recommendation that our user ignores are very important, because we can also tell the NLP models that we want to obtain concepts that are similar to certain concepts, but also that are as far as possible from other concepts. So we would use these rejected terms in that sense. Okay, so We have performed a preliminary validation, and we have used an industrial project which dates from 2015 and was developed in the context of a water supply and sewage company in Malaga, in the south of Spain. And their goal was to introduce a notice management system for incidents. So since the project has already been developed, we had access to the domain models that were manually produced. And we also had access to the documentation that in 2015, the company provided. And this was a presentation consisting of 21 slides, some paper forms that we wanted to have replaced with this new information system, and a software requirement specification that consisted of over 7,000 words. And with this case study, we would like to study the recall, the precision, the performance of our approach, and also we would like to see from which source of knowledge these suggestions are coming. So this is the domain model that was manually built. And to evaluate our approach, what we have done is to automatically reconstruct the domain model. So we try to simulate the behavior of a designer automatically. We started from 5 partial models. So we have performed this process 5 times, one starting from each one of these partial models. And for instance, in the case of client, we start from a single class client with no attributes, no association, anything, nothing else. And what we did is to run our model recommendation engine and our approach and accept all the concepts that were in the original, in the final model created by hand, and reject those that were not. And you can see that this is the worst case scenario, because in the end it was overrun automatically. We assume that a user could not rely only on the model recommendation engine, but he could also, or she could also contribute to this by creating some of the concepts by hand, so that the partial model is richer, and the richer the partial model is, the more meaningful the suggestions are. So let us now explain the results that we obtained after this. So we obtained a recall of 62%. So we were able to reconstruct 34 out of the 55 elements. When I talk about elements, I mean to classes, attributes, and associations. And this is the model that we were able to automatically reconstruct with no human interaction. With respect to the precision was for over 4%, which may seem very low, but this is because we are being strict here, and we are counting the exact precision. But let us also say that we query the model. As I said, we performed 5 case studies. This is the 5 case studies. No, we did 5 different experiments for this case study, and we computed the average. So on average, for each partial model that we reconstructed, the recommendation engine was queried around 15 times, and we obtained 20 suggestions per query and per source of knowledge. This means that there were over 600 suggestions received, out of which 25 more or less were accepted. This is looking at the general numbers, but if we look at the number of accepted suggestions per query, it was 1.79, which means that for each recommendation, we automatically accepted 1 or 2 suggestions, more or less. So with respect to the source of the accepted suggestion, we observed that 85% more or less of the suggestions were coming from the contextual source of knowledge, and only 14% from the general source of knowledge, which is in line with what we expected. And with respect to the performance, we observed that all the components in the model recommendation engine took under 1 second, but the critical point that we wanted to explore was the querying of the NLP models. So the training and loading and querying of the contextual models each of these steps took only a few milliseconds, because in the end, the corpus of text of the contextual knowledge was pretty small. But when we talk about the general source of knowledge, which is the model trained by with the whole data from Wikipedia, the loading of this model took 32 seconds. That's done only one when the engine is initialized, but still 32 seconds. And the query of the general knowledge each time usually takes a few seconds. We have used right now the Python implementation, but we know that there is this C implementation that the creators claim to be more efficient. So we plan to move to that in the future. And to conclude, let us say that we have presented a model recommendation engine, which is fed with the textual description of a business domain or a domain, and it generates auto-completion for models under development in the form of recommendations that are provided to the user, and that the user can accept, reject, and also this model recommendation engine learns from the interaction with the user. So we think about this as a first step towards modeling a system that will be able to build models which are of higher quality and faster. And for the future, we would like to integrate different types of information into our approach. For instance, we could take past models built by the development team or the domain modelers and learn from that, and not only semantically, but maybe also about the structure of those models. We could also incorporate ontologies as an extra source of knowledge. And we would also like to explore the usability aspect of our approach with empirical study with real users, and would really believe that they will provide useful feedback. We would also like to refine the techniques presented in this paper. For instance, for now, we have used Globe, but for the NLP components, and WordNet for the morphological analysis. But we know there are many other language models that we could try, for instance, WordPeg, BERT, any of these, and see if they are more or less suitable for our approach, or if we can even combine them to provide richer suggestions. We would also like to explore these for different type of models, for instance, activity diagrams, sequence diagrams, and so on, and for other modeling languages. And finally, we would also like to refine these our engine with the more slices, with the providing new recommendation for each slice. So yeah, we know that we can still explore more possibilities there. And I think this is all from my side, and thank you very much for your attention.
Thank you very much for this interesting and very time-oriented presentation. So I directly want to go to the questions, and I already have one in the Q&A. And the question is, how do you automatically differentiate if the recommended words are nouns or verbs? So there's also an example given. For example, on your slide 16, you have pilot as a noun and pilot as a verb. So how could you differentiate this?
We use, in this case, WordNet, which allows us to know the tag of the word. So in the case of those words, WordNet would tell us that it could be a verb and it could be a noun, and we knowing this, we know that, for instance, for nouns, we can recommend new classes added to the domain, and maybe for verbs, we can do some other recommendations that are for associations and so on. So yeah, but it for short, yes, we use WordNet to do this type of analysis.
Okay, thank you. And there's already another question. So it's mainly referring to entity relationship models. Yeah. So, and here the question says that in terms of entity relationship models, there are studies about the resemblance of English language structures. So nouns, verbs, adverbs, and so on and so forth, and the model elements like entity types, higher order relationships, and so on. And this resemblance is a very strong argument for the ER model. So in comparison, how do you consider the context in which the words appear for generating your machine-learned recommendations?
Can you repeat the question, the last part?
So it's about resemblance, yeah, about like the English language structures and the model elements in an entity relationship model. So for example, there's this old study of Chen entity relationship diagrams and so on. And then the question is, how do you consider the context in which the words appear for generating your machine learned recommendations? So it's about the context of the words.
Yeah, I guess the question refers to the NLP models. So if this is, I mean, this is what I understand. So the context is given by the NLP models. So in the end, this globe approach, what does is it analyzes the corpus of text and somehow defines a distance metric between words. And the more the words appear in the same context, the closer they appear together in the text, the shorter this distance is.
Mm-hmm.
So
maybe also, yeah. I mean, Sebastian Dink asked the question, so maybe you want to also comment on this. I think you can, right?
Can you hear me?
Unmuted. Yes, yes. Mm-hmm.
Okay, well, thanks. So what I meant was that in the previous studies, they looked at whole sentences and actually also the meaning behind them. So whereas you seem to be looking only at the words in isolation. So wouldn't it be better to take care of the whole structures and the whole sentences rather than dismissing them?
Yeah, now I know what you mean. Yes, that could be an extension to our approach. The thing is that, of course, right now we are ignoring all sentences. We're not paying attention to the semantics at all. Yeah. So we simply focus on the frequency in which words appear together, and we assume that, for instance, if we are talking about airplanes and planes and so on, there will be related work, and if we are talking about banks and finances and so on, the vocabulary and the terminology would be similar there. But of course, we're not right now paying attention to specific sentences or analyzing the semantics of them. That could be something additional to complement our approach. Yes.
Yeah, thank you.
Thanks.
Mm-hmm. Okay, thanks. And there's also then another question by Lars. Anyway, you're a speaker, I think you can always ask the question.
I also cannot ask it vocally.
Yes, okay. Please.
So it's just hooking into the first question. Many words are ambiguous regarding their type. For example, marks, run, and so on are both verbs and noun. And if you use WordNet, I wonder how you figure out which of the type it is really. This is what it was not clear to me, at least from the first explanation.
Yeah, but if one word can be of different types, we consider them both. In the end, what we do is we take the recommendations and say we need nouns to recommend new classes to add to the domain, and therefore, if one concept that is recommended is a noun, even though if it can also be a word verb, if it is a noun, we recommend it as a new element to add to the model of type class. So yes, we that is not a problem for us.
Okay, I see.
All right, thank you. So are there further questions? And maybe it's more like a mixture of questions and comments. So I appreciate, so in your future work, you mentioned that you also plan to do user empirical studies. So I think that's very important to also learn what the users can actually do with that. Maybe, do you want to comment a bit further? Do you already, did you already think about how to design such a study? So what would you ask them? So how could you do that?
Yes. In that sense, we have plenty of ideas. First of all, we have, yes, to design the study, but we also have some questions that we would like to ask our users. So we first of all, we want to have to provide right now we have a proof of concept. There is some person that we have recently hired to develop this further. And we have some options, design option that we have to take. For instance, from where are the recommendations coming? Contextual knowledge, general knowledge. How can we provide these? Should we provide the two of them to the user? Should the user prefer to receive just one list of recommendations, the recommendation from all sources separated, or so on? So that's the first step before designing the actual empirical study. And then for the empirical study, we don't have concrete plans yet, but most likely we will use some of our students at our universities, but we also would like to rely on the knowledge of our colleagues, who are more expert into modeling, and maybe, if possible, to ask also some of our industrial partners to help us with this, because in the end, their feedback would be more valuable than those from people who are not working on this.
All right, yeah, thank you very much. And also, I think we've now at the end of this very interesting sessions, and I would like to thank the speakers again, and also the audience for this very nice discussion. And then have fun in the other sessions. See you.
Yeah.
Bye.
Thank you.
Thanks all from my side. Bye bye.
Okay. Close up this one.